I'm here with you, and sorry for the language barrier. Unfortunately, I don't speak Turkish, so I have to do my talk in English. If at any point I'm not clear, in general you have questions, please feel free to raise your hand. I want to keep it very informal, and I hope my talk is going to be informative. And as I said, please feel free to ask questions about the content or how I'm presenting them or anything else. All right, so I'm going to be introducing SparkR. So that's going to be the focus of my talk. However, I would be more than happy to answer other questions about Spark or my employer, Databricks. Before I get into this, I'd like to do a show of hands. So please raise your hand, whichever applies to you. How many people here are using Spark? Raise your hand. So I would say maybe about 10. So you're using it. How many people here are R users? You use R for your work. Maybe about also 10 or maybe less. Okay, cool. All right. So I hope this is going to be a good introduction for both Spark and R users in the crowd. I have prepared a talk that includes introduction to Spark, like the internals of Spark a little bit, and why it's faster, and why the architecture is the way it is, and introduction to SparkR, including its architecture and API, and then some hands-on demo of the API. Now, I want to ask you to tell me if you do not want to go through the introduction of Spark. So raise your hand if you do not want me to go through Spark introduction. Okay, so maybe 6 people. So for the benefit of the rest, I know some people here are already familiar with Spark. I'm going to do some introduction of Spark. I'll try to make it quick, but I think it'll help for the second section of my talk, which is introduction to SparkR. So a bit of introduction. Databricks is the company that was started in 2013 by creators of Apache Spark. There were 6 people, 1 professor and 5 PhD students and researchers at UC Berkeley who worked on Spark, and then they decided they can take it to the next level by starting the company. The company is focused on making big data simple. That's kind of an interesting claim, and we do that by offering Spark as a service in the cloud. We are the largest contributor to Apache Spark, and through contribution, we drive the roadmap or the future of Spark, but it's only through contribution. Apache Spark is an open source project, and anyone can contribute to it. Okay, so as I said, this is the outline of my talk. First, I'll go through some introduction of Spark, an overview, the programming model, and why it performs better than Hadoop. Then we do a deep dive into SparkR. I present the SparkR architecture, how it fits into the Spark architecture, an overview of the API, and I'll give you some things about the future roadmap of SparkR. As you know, it's a young project. And then last, I'll do a hands-on demo. I'll first show how we see our customers use SparkR, because we offer SparkR. We were the first company that offered commercial support for SparkR, so we know how customers are using it. I'll show you how they do it, and then do an API do a demo of the API, and then at the last section, if time allows, I'll do a machine learning demo that kind of relates to SparkR. All right, let's get started. So we like to mention this recently. Fortune magazine called Spark the Taylor Swift of big data. It's very popular, everyone likes her, and everyone seems to like Spark. And we are happy about that. But why? There are many reasons. It is a general computing engine. One meaning of that is that it doesn't care what storage you're using. Any storage, you can use it with Spark. And in the same sense, it doesn't care what API you want to use. If you want to use Scala, Java, Python, or R, or even SQL, you can use the engine. So the engine can be programmed with many interfaces. And there might be other interfaces coming in the future. So it's general in that sense as well. It's also general in another sense. There are many different workloads or types of processing that can be done in Spark. You can use Spark for SQL, as I mentioned, streaming, which is different style of processing, machine learning, and graph processing. So it kind of accommodates all those types of workloads as well. And also it's faster. It's between 10 to 100 times faster than Hadoop, depending on the type of Hadoop MapReduce, I mean, depending on the type of workload. I'll offer more details about that. So the core concept of data processing is Spark is around this RDD. RDD stands for Resilient Distributed Data. That's a term Matei invented in his first paper. If you're interested into like the research part of it, I encourage you to read that paper. It's very interesting to compare which parts of that paper are still valid after I would say 4 or 5 years. So an RDD is a collection of objects that can be stored in memory or disk. So it's just referring to data. The data can be in memory or on disk. And then you can apply functions on the distributed data. You can transform them, you can filter them, you can collect them, you can do whatever you want. And the key feature of RDDs that makes them resilient, the first R, is that they are fault tolerant. Meaning that if you are running a Spark on a cluster with 1,000 machines, and the probability of failure is going to increase as you add more and more machines, you're going to get nodes disappear from your cluster. Spark can work around those failed nodes, and RDDs will reconstruct themselves if nodes fail. So let's walk through a simple example. You might have seen these slides, but it's still good to refresh your memory. Imagine a simple cluster that has, say, 4 computers. One of them is going to be designated as the driver machine. It's not nothing special. It's just a driver for that application. So I can read data from distributed storage into an RDD with a simple, call text file. Then basically this just gives me a base RDD. It doesn't do anything. Spark RDD transformations are lazy. It means when I make this call, nothing actually happens. I just told Spark that, read data from that path. Then I can perform other transformations on my RDD. Here I'm filtering, and I'm passing it a lambda function in Python. For those who are familiar with Python, it's very natural in Python, and that's one of the reasons people like Spark, because they can just use functions like that. You don't like in MapReduce you have to implement. In Hadoop MapReduce you have to implement a special class to be able to do like a filter in native language like that. So then I do another transformation, still lazy, nothing happens, just get a pointer to another RDD. And then basically another transformation, I'm splitting, let's say, each line by a tab, and then I call cache. Up until here, nothing has happened, as I said. The last command tells Spark, whenever you do operate on this data, keep messages in memory. So we'll see what happens. So then I call count, which is an action. So count is the action. An action is different from a transformation in the sense that it actually triggers the execution. Once that gets triggered, Spark will start to compute the result, and in order to do that, it goes back in the lineage of RDDs all the way to distributed storage. And because it has been told to cache messages, while it's doing that, it will keep them in memory. So the next time we do anything with our RDD, so let's see how. So basically this animation shows what happens. The driver tells the worker machines that start doing your job. Each worker will read a block of distributed storage, and then the results are sent back to the driver. And meanwhile, caches are created on the worker. So the cache is on the worker. There is no data in the memory of the driver. It's a distributed cache. So the next time if I call count with a different function, it's going to be much faster. Maybe 100 times faster, because we don't touch the disk anymore, which is the bottleneck. Okay. So basically, with this, and this is an old benchmark, we can do a full text search of Wikipedia in less than a second when it's cached. And you'll see that. And we could also do that with terabytes of data. All right. So let's see what happens with the RDD lineage. As I said, RDDs are fault tolerant. It means if, so basically an RDD is represented with a circle, with a block like this. So it has 3 partitions. Okay? And we are doing some transformations. We do a map and then reduce and a filter. If at any point one of the machines fails or disappears or crashes, the RDD, because it knows the lineage back to distributed storage, and the distributed storage is assumed to be fault tolerant, for example, HDFS has replication, it'll reconstruct the missing parts. As a result, we can be much faster. This shows itself dramatically when you're doing iterative jobs, which is a good example for machine learning. Many machine learning algorithms are iterative. You have to perform the same optimization functions multiple times until your model converges to the optimal model. The more iterations you do, the more the gap between the performance of Spark's in-memory computation with Hadoop's on disk becomes. Okay, so just to hide, this was the message we always talked about, that with in-memory caching you can get great performance. As a result, there was about a year ago or 2 years ago, people always assume Spark is good only if you can cache your data. If you don't have enough, if your data is very large and you can't cache it, or you don't have enough RAM, or you don't need caching, there's no point in using Spark. So what we did, we didn't think so, because we think Spark is even faster for on-disk than Hadoop MapReduce, so we participated in the terabyte sort benchmark. That was 2014, and 2015, I don't think it is announced yet. So in 2014, Spark became the winner, and so this was the 2013 record. Hadoop, so Yahoo held the record with Hadoop. They used about 2,100 machines, and they could sort a terabyte of data in 72 minutes. And that's on disk, you don't need to cache it here. With Spark, we used about 200 machines, and you could sort it in 23 minutes. And this is, again, it's not in memory, it's completely on disk. So even when you're doing on disk, Spark is faster than Hadoop MapReduce. By the way, we also sorted a petabyte just to test our scaling, and you can do it in 4 hours. But the benchmark is only about a terabyte. Okay, so this everyone is familiar with. You saw it in other slides. This is the architecture of Spark's libraries. I'm not going to go into details of that. But the important point is that you can switch between these components, and that's a great advantage that we hear from many users of Spark. That we ask them, why do you like Spark? And they tell us, well, we can use all these components together. We don't have to have one system for SQL, another system for streaming, and another system for batch. You can do that, but then the problem is that if you want to mix those workloads, you have to save data and read it again. It's slow and it's not convenient. Here's an example, a few lines of code. The user is basically reading data with a SQL query, again from a Hive table. This is a Hive table. And then gets back a data frame. I'll talk a little bit more about data frames and what they are. And then you can just train a machine learning algorithm on that data frame. So basically you switch from Spark SQL to Spark MLlib. And then you can apply that model on a live stream of tweets. So basically we seamlessly switch between different components, and you don't they're all the same API. You don't have to do anything special about it. The great thing is, all of this, because the engine was developed to be general and independent of storage, can be done both efficient in terms of execution and usage, but also efficient in terms of implementation. So this is the number of lines of code of some of the existing big data systems in the Hadoop ecosystem. As you can see, Spark is fairly small in terms of number of code. That is mainly because Spark uses Scala, and Scala is very, you precise, and you can write big programs with few lines of code. So that's the expressiveness of the language helps Spark here to keep a low number of codes. But still, it's interesting to compare the number of lines of code. This is important because the more lines of code you have, the more likely you have bugs in your code. So smaller code is something to be proud of here. Let's compare them. Storm is streaming, Impala is SQL, and Giraffe is for graph processing, and Hadoop MapReduce is just a computing engine. So we added Smart Streaming with which is about 70,000 lines of code to Spark, with I think maybe a few thousand lines of code. And then Impala is a little bit more than 80,000 lines of code, maybe 90,000. And then that's the amount of code in Spark we had to add to support SQL on top of the core engine. And then GraphX is another big project for itself. It's about 80,000 lines of code. And you can see, sorry, the Giraffe, and then you can see GraphX on top of Spark. It's fairly small. The reason I bring this up is that this can apply to your application. Instead of building your application from scratch and writing thousands of lines of code, you can take advantage of Spark's libraries and engine to implement it with much less code and basically save time. This is another important factor of the design decisions of Spark, the fact that it's general. It means a lot of applications can use it. All these applications are basically sitting on top of Spark's API. Also, different frameworks can run Spark. Mesos is a resource management framework. Yarn is another resource management framework, and many others already have support for running Spark in them. And you can read data from multitude of data sources. So by keeping the Spark design kind of concise and small and limiting it to just computation, you can use it with different sources of data in different applications and in different frameworks for execution. Needless to say, it's a very large community. Many companies are contributing to Spark. Many are actively looking for Spark developers. So if you're a Spark developer or have contributed to Spark, chances are these companies are looking for you. You'll get emails from their recruiters. There's a lot of contents and talks and resources and tutorials available if you're interested to learn about each one of those components. There's this website called sparkhub.org. It tries to aggregate different sources of information about Spark. So check it out, see if you can find what you're looking for about Spark. Okay, so I'm going to go to the second part of my talk. That's like basically the main part. Before that, I want to make sure there are no questions or there are not unclear parts about Spark. Any questions? Okay. So, Spark and R. R is an interesting language, and it is very rapidly growing in popularity. Many data scientists' favorite language is R. So there's basically two languages that are very common for data science: it's R and Python. We ask data scientists why they prefer to use R, and we basically compiled a list of things they like about R. These are advantages of R as a language or a runtime. By the way, when I say R, I may use it to refer to both the language, which is just the programming language, and a runtime, which is the engine where you run R. There are different runtimes for R. The most common one, the most important one, is called GNU-R. It's basically the standard runtime, and that's what almost everyone uses. There are other runtimes. There's Rengen that is implemented in Java, basically. It's in JVM, but it tries to run the same R code. But anyway, so the advantages of the language and the runtime is that the runtime is open source. The GNU-R is open source and free. You can download and start using it right away. Whereas competing systems like MATLAB and SPSS and others, you have to pay a hefty amount for the license to use the software. So that helps. It's a very dynamic language. What does it mean? you can change everything in the language while you're using R. As a specific example, when you are doing a loop, a simple loop in R, and you're iterating over a number of integers, inside your loop, you can change the type of your loop variable to a string. So the type can be changed kind of freely like that. And many other things that you can change about the environment. And that helps. You can do interesting things with that dynamism of the language. And it's by design. The environment is interactive. It's designed to be interactive. The API is designed such that you use them basically with this assumption that people are going to use them interactively. They're very concise. You don't have to like pass in tens of arguments to run a statistical model. You can just pass the arguments you need, and everything else is assumed to be the default. So that helps because statistical analysis is by nature interactive. The R comes with a rich ecosystem of packages, so that helps a lot. Many things, whenever you want to, do one sort of analysis or another, just search for a package that has implemented that algorithm in R, and you're very likely to find one. You can easily install it and start using it in R. The language, the runtime and the language came with pretty powerful visualization infrastructure. As a result, there are many visualization libraries people use. It's one of the best environments to do data visualization, especially for statistical analysis and data exploration. Also, data frames make data manipulation and data massaging very convenient and easy. Data frames were invented in R, but they turned out to be a very powerful concept. So other languages have copied them. For example, Python, there's a library called Pandas, which is basically tries to copy or implement the concept of data frames in Python. How many here know what a data frame is? Okay, so I need to explain it because about half or more than half don't know. A data frame is very similar to a relational table. Just like a table where you have multiple rows and each row has multiple fields and each field or column can have different types, the data frame can have multiple rows and each row has different fields. However, to manipulate the data in a data frame, you don't need to use SQL. You can use functions to filter data rows or filter columns or do summaries or aggregation. So it's like a table that is exposed as a first-class object in your language. And that turned out to be very convenient and powerful for data science. No one knew, but it seems it was the right decision or right design. So as I said, in Python, data frames are becoming very popular. Pandas, data frames are being used almost everywhere now. Also, Spark kind of learned from R and Pandas and implemented data frames. Obviously, Spark's data frames are distributed. We'll talk a little bit more about them later. Then finally, R is the language that is being taught for statistical and computing students in many universities these days, at least in the US. When students go to any statistics programs, they come out with R knowledge. I don't know, I learned that it's not the case everywhere, so I wonder, is anyone here doing computer science or statistics? Did they teach R in school? I see. Cool. Okay, so it is very popular in the US and some of the European countries, in Australia and New Zealand, where R was invented. And that helps because there is a shortage of data scientists these days, and every year there are more and more people with R knowledge that enter the data science market. Okay, so these are all the advantages of R. However, there are some disadvantages too. The most important one is performance. And the performance disadvantage or problem is kind of not easy to fix. One of the reasons for the performance limitation is the design of the language. As I said, the language is very dynamic, and that's good. It has an advantage and a disadvantage. As I said, the advantage is that you can do very interesting things. It's very convenient for exploratory and interactive analysis. The disadvantage is that the runtime can't do optimizations. The example I mentioned was that the loop variable can change while you're doing you're going through your loop. The type of it can change. So the runtime cannot assume that the loop variable is going to have the same type. So every time, every iteration, it has to check its type, and that takes time. So that's the language design cause of performance limitation. The other issue is the runtime implementation itself. The GNU R runtime is not the most efficient implementation. It is single-threaded, and everything has to fit in memory. Some of the new runtimes that are being implemented for R try to address those issues and problems, but they haven't been complete yet. So you can't just start using them. Most people, almost everyone I know, uses the GNU runtime. Okay. So we have a great language. Many people know it. It's very popular. There are many packages in it. It's used for visualization, but it has performance limitations. And every day, the amount of data is growing. So we need to use R with more and more and more data. So when we ask data scientists who use R, what would be your ideal world? You know, what do you like? They say we want to use R, but we need to be able to use it with a lot of data. Basically, they want that performance limitation resolved. This is kind of ambitious, and I explain why. So basically, they want R's flexible syntax. That's doable. The rich ecosystem, that's hard. The interactive environment, that's doable. Scalability to up, basically scaling up and scaling out, that's also doable. And integration with distributed data sources, that's also doable. So let's go through them. Scaling up means being able to run on a very large machine. Imagine you have a machine with 20 cores or 18 cores, and you have 2 terabytes of RAM. You can get these machines on Amazon right now. The problem with R is that even on that single machine, R will not be able to take advantage of all the cores. It's a single-threaded, single-core implementation. So you can't scale up. Scaling out means I have so much data, they will not even fit on any large machine. I need a cluster of maybe 100 computers to fit my data. So I need to scale out. So that's the distinction between scaling up and down. Among these, the one that is difficult is basically integration with all the packages. And I'll tell you why that is difficult. So, what I'm here to say is SparkR can address most of those requests. What is it? SparkR is an R package, basically, to think about what it is. It's an R package, but it's distributed with Spark. So if you check out the Spark source code, there's a directory called R that has R code in it. So it's distributed along with the rest of Spark. It offers a front end to Spark's API. And by that I mean you can call Spark's API in your R environment. And it exposes Spark's data frames in R. And offers some convenient functionality for converting data between R data frames and SparkR data frames. So basically with SparkR, the attempt or the goal is to get all the advantages of Spark and all the advantages of R. Some things are going to be easier, some things are going to be harder. For example, as I said, the integration with all the existing packages is a little bit harder. But the interactive environment, or being able to read data from all the existing sources that Spark supports, or being able to scale up and scale out, is doable, and it's already done. Okay, so let's talk about the SparkR architecture. You remember that Spark architecture that consisted of a driver and a number of workers? So this is that, but including R in it. SparkR basically sits in the driver. There's no R code running inside the workers. In the workers, it's only JVM running. In the driver, there is an object called R backend running in the JVM. And there's a separate R process that basically is your R environment, and that's where you will be using SparkR. And then the R process and the R backend can talk to each other using a custom protocol over local sockets. And basically the job of R backend is to translate calls and data from the R process to the JVM. So basically, when a user types a command in their R environment, that command gets translated, sent to the R backend, and the R backend will translate it to native Spark calls, which are implemented in Scala, and then the rest will be executed just like any other Scala command. So when you're using SparkR, the performance is just like using Spark. But the environment is R. You're interacting with it inside R. So as a result, because everything is in, the workers are running JVM, the data, distributed data, you remember the cache data that the workers kept, that is kept in the JVM. And you can use all of the data sources that you're used to with Spark. So far, is there any questions about the architecture? I'll be happy to answer. Yes?
Does Spark use Akka framework to distribute tasks to workers?
So the question is about how do tasks just go from the driver to workers? It used to be Akka, but I think we replaced it with an internal many-based. So that part is not part of Spark's exposed API, and as a result, internally it can change from one release to another. Basically, the users Spark users don't see those calls going on. Any other questions about the architecture of SparkR? Okay. So let's do an overview of the API of SparkR. This is kind of a broad categorization of the API. What I'm going to go through each section and introduce a few calls in that section. And by doing that, by the end, hopefully we can become SparkR programmers. The first category of calls is I/O. These are used to read data from distributed storage, or to write to distributed storage, or to communicate data between the JVM and the R process. The second category is related to caching. You can use these to basically control whether your data needs to stay in disk or in memory. That's distributed data. We have utility functions. These are basically the ordinary functions that you're all familiar with when you use R. And you have access to those utility functions on Spark DataFrames. So basically those are the re-implementations of existing R functions that can operate on Spark DataFrames. ML, basically this is the interface to Spark's machine learning library in R. So far only the generalized linear model family has been ported. The rest of it is going to be ported. DataFrame API, these are all the APIs that you can, like all the methods you can use to manipulate and like filter and transform and aggregate and summarize Spark data frames, distributed data. And then SQL. As I said, a data frame is just like a table. So you can manipulate it using API in native language, or you can manipulate it and query it using SQL. And we'll see how you can do that. Okay, so before I go into details of this, let's introduce the SQL context. If you use Spark, there's a Spark context. Like in Scala or Python, you need to create a Spark context. And then once the Spark SQL was added, another object was introduced called the SQL context that basically wraps around the Spark context. In SparkR, if you want to start using SparkR, you first need to create a Spark context with this call, basically SparkR.init. If you're running in a cluster, you pass arguments to this init that points it to your cluster's master. And then you use that Spark context and initialize a SQL context. And you don't need the Spark context anymore. So from now on, all your interactions with SparkR is going to be through the SQL context. Basically, all the methods in SparkR either take a SQL context or a DataFrame object. Okay, so imagine we created a SQL context in SparkR, then how can we use it? The first thing we can do is read data. The most important method to remember for reading data is readdf. Readdf is kind of a general method. It allows you to read data from many sources in many formats. Basically, all of Spark's data sources can be used with readdf. The signature is very simple. As I said, the first argument is going to be SQL context. So you pass it. This way, if the function knows which cluster it's talking to, then you give it the path, and then you give it the source. Like, is the data in CSV? Is the data in JSON? Is it in Parquet? Is it in Avro? Do you want to connect to a database and read data from an existing database? Is it Cassandra? All of the existing Spark data sources, if you just pass their names here, and readdf will be able to connect to them and read them. Okay? There is if your data is JSON, instead of readdf and then source equals JSON, you can say read JSON file. Equivalent. And if it's Parquet, you can use Parquet file. The opposite is writedf, which helps you write data. So if you have it, this time it takes a data frame. It doesn't take a SQL context. So if you have a data frame, you want to write it to a distributed storage or your database in any format, you just need to use writedf. And similar to Parquet file, we have save as Parquet file here. So these are connectable if you just specify source as Parquet. So the readdf and writedf basically allow you to read data from distributed storage to your workers or write it from workers to distributed storage. It does not bring data to the R process. To do that, to communicate between the R process and JVM, you use collect and create data frame. Create data frame takes a SQL context and a local data frame. This is an R data frame. It is not a distributed data. And then it returns a Spark data frame, which is distributed. And the opposite, if you call collect on a Spark data frame, it will do two things. First, it will transfer all the data from the workers to the driver, and then it will translate the data from the JVM to the R process on the driver. So at the end, you get a local R data frame. So let's see how those work. As I said, readdf and writedf are for reading and writing to distributed storage, S3 or HDFS or Cassandra. And the opposite, the other two calls, which were collect and create data frame, work between R and JVM. So when you call collect, data moves from JVM to R. When you call create data frame, it goes the opposite direction. This is basically all the I/O methods you need to know about Spark. Okay, now caching. The most important function to know about Spark caching is persist. And funny, most people don't know about it. Persist is a general function that takes a data frame and a storage level. And the storage level can be one of these strings. And it basically tells Spark to keep the data in that storage hierarchy. So by default, a data frame, which is very similar to an RDB, is on disk. So there's no caching happening. So if you call persist data frame disk only, basically nothing special happens, but you can make that call. The next level, you can tell persist on memory and disk. That tells Spark, try to cache it. But if it doesn't fit in memory, split it to disk. Don't fail. Even if none of it fits in memory, the backup plan is operate on it on disk. And then, similarly, you can have memory and disk serialized. It is similar to memory and disk. The difference is that the data is going to be in serialized format. It's not in Java object. Okay? And then we have memory only, which tells Spark, try to cache all of it in memory. If it doesn't fit, fail. Send an error, say, data didn't fit in memory. And similarly serialized. And then there's an off-heap option, and that's one example of using it is when you use Tachyon. You can cache it in off-heap with a system like Tachyon. How many people here have heard of Tachyon or know what it is? Cool. All right, so cache, which is the most commonly known function in Spark, is basically equal to persist with memory only. Okay, so now you know what the other equivalent, the other members of this caching family are. As I said, Spark's data frames are basically tables. So you can also use cache table to cache a table, and then you pass the table name. This is caching API. Any questions about that? Right? Next, the DataFrame API. So the DataFrame API in SparkR is designed to be very similar to the native R DataFrame API. So basically, the goal is, if you're using SparkR and you're using a SparkR DataFrame, ideally the user shouldn't even notice they're operating on distributed data. That's ideal. You're not there yet, but that's like the direction the development of SparkR is going. So if you are familiar with the dollar in R, you can select a column by using dollar name of that column. You can create a new column in your data frame by basically assigning something to it. Here I'm getting a column and adding 1 to it, and then assigning it as a new column in my data frame. So Spark data frame at the end of this line will have an additional column. The way this works, basically when you call dollar on Spark data frame, you're calling it a special function that is implemented by SparkR. And then when you call plus, that's also not an ordinary plus. That's a special plus that takes a column and an integer and then returns a column. Okay? The bracket is also one of the convenient ways of selecting columns or rows in R, and that is supported in SparkR. Basically, you can use the single bracket, square bracket, and pass it a number of columns. Basically, it takes 2 arguments separated by comma. The first one is an index to rows. The second one is an index to columns. So here I'm basically selecting 2 columns, date and type, and putting them in a new data frame. Subset is very similar to the square bracket. Some people prefer this syntax. So you can pass, so this syntax actually is missing here. I need to pass the recent data. So the first argument needs to be a data frame. Basically, this gets a data frame that with the data only for this date. The double brackets returns a single row. And also other functions, the utility function that I told you, like names. If you want to assign, rename your data, you can basically, this is kind of weird for other languages, but in R it works. You can call names on data frame and it returns the list of column names. And you can also assign to names, and that will basically change the names of the columns. Dimensions returns the number of columns and rows in your data frame. Head basically returns the first few rows. So this is a kind of a complicated example. Here I'm taking a Spark data frame, subset data frame, and then grouping by date. Okay? And then I'm counting the number of rows that fall into each grouping. And then I collect it, and then I call head. So basically I'm chaining a bunch of functions into each other. This is very common syntax in R. It's not very convenient that you kind of have to chain functions inside each other. You have to keep track of your closing parentheses. To make it simpler, people use some packages. I'll show you how to do that. So let's quickly do ML. As I said, GLM is already implemented. I encourage you to go read. We published a blog post. My colleague who implemented GLM in SparkR published a blog post with an example of how to use GLM. I encourage you to go read it. Just Google for SparkR GLM and you'll find the blog post on Databricks website. It's just basically 3 functions. The GLM function, you can pass it a formula, just like R. A data frame and a family for your loss function, and then you get a model of that, you can summarize it, you can do prediction on it. So the next one is SQL. This is kind of important, so let me spend a minute on it. As I said, again, Spark data frames are just like tables. So you can take a data frame and tell Spark, hey, I want you to treat this as a table, and that's done through a function called register temp table. It tells Spark, hey, this data that is in memory or on disk or whatever, and I refer to it by with this data frame name, I want to refer to it with a table name as well. So you give it a table name, a data frame and a table name, and from that point on, this is the name of your table. And then you can call SQL, give it the SQL context, and then any SQL query you want against that table. So I called it logs table here, and you see I'm querying logs table. And it returns a data frame to me again. It's very convenient. It's extremely convenient to be able to move between the API and the SQL like this. And then the opposite of register temp table is table. So if you have a table in Hive or a temp table, you can get it back as a data frame by calling table. So you can see that I'm basically registering a temp table by applying the function of data frame here. Okay, so it seems now it's time for a break, the first break. I'll continue this after the break.